Well, hi there once again. Thanks for tuning in to another pre-calculus review video here for your midterm. This one is going to be concerned with the topic of polynomials, and we'll divide this topic into three subtopics, I guess you could say. First one is the end behavior. We'll be describing the end behavior of a polynomial. Kind of an important feature of polynomials is what the ends of the graph are doing. And the second subtopic, I can't remember what the second one is right now. Hang on. Well, the third one is the asymptotes of a rational function. That's not exactly polynomials, I know, but they were in the same chapter in the book, so we'll talk about them here too. Oh yeah, I remember now. The second topic is finding the zeros of a polynomial. Extremely important. Okay, so let's get started with describing the end behavior of a polynomial function. All right, well, the end behavior of a polynomial function is dependent upon two things. Number one, the degree of the polynomial, if it's an even number or it's an odd number. Okay, you can kind of divide them up into those two categories. Here's a graph of a couple of even degree polynomials. You can see a positive one is in the black and a negative one is in the white there. And one of the things you should notice about the ends of these even degree polynomials is that they both point in the same direction. All right, and if it's a positive even degree polynomial, it points up. That is, the ends point up. And if it's a negative even degree polynomial, the ends point down. Okay. By the way, you can determine the whether it's even or odd. Whether it's positive or negative by the sign of the leading coefficient. Okay, that goes for all polynomials. So there you go. There's a picture of some even degree ones. Some odd degree ones. Here's a graph of a couple of odd degree polynomials. Once again, the positive one is in black and the negative one's right. And you can see that the positive one has the right end going up and the negative one has the right end going down. All right? So that pretty much covers everything. There's either even degree or odd degree, and they're either positive or negative. And so these are kind of the four different possibilities that you can see. Well, you don't always, unfortunately, have a graph. Sometimes you just have to go by the equation. So let's take a look at a couple of equations. So here's the first one here. Polynomial function of x, p of x, equals 7x to the fourth minus x cubed plus 2x minus 1. All right? Well, we can see just from looking at this equation that it is an even degree polynomial. That's right, because the highest exponent is a 4. And it happens to be a positive polynomial because the leading coefficient is a positive number. So that must mean that both ends are going up. All right, that is true. We don't even need the graph. I just wanted to point out here, however, that sometimes mathematicians have curiously formal ways of saying sometimes very obvious things. Such as, well, there's a mathematician who lives in my house. His name is Professor Finn, and this is how he would say this. As x goes to infinity, y goes to infinity. That means the right end is going up. And as x goes to negative infinity, y goes to infinity. That means the left end also goes up. Okay, so they have kind of funny ways of saying the very simple ideas. Let's take a look at another polynomial, such as p of x equals 4 minus 2x cubed. All right, this is an odd degree polynomial, clearly. The only exponent is a 3. It's an odd number. And but it is a negative polynomial because the leading coefficient is negative 2. Now, just keep in mind, the leading coefficient doesn't mean the first number necessarily. It means the coefficient of the term with the highest exponent. So in that case, this is negative 2. So it's a negative. It's odd. It's negative. That means the right end is going down. Therefore, the left end must be going up. However, Professor Finn, he would describe it this way. As x goes to infinity, y goes to negative infinity. And as x goes to negative infinity, y goes to infinity. All right? So that's basically saying the right end is going down and the left end is going up. Okay, well, I think that's about enough on the end behavior of polynomials. Thanks. So here we go with the topic of finding the zeros of a polynomial. That's zeros, alrighty. And That is going to be, we're going to talk about two different ways to do this. One is factoring, and the other one is using the synthetic division process. Now, finding the zeros can be a rather large topic, so I'm going to have to limit the scope here to make it a useful video, and to keep it focused on what the final is going to be. All right? So first let's talk about factoring. All right? Let's take one polynomial that's already been factored for us, and that really does make it pretty easy. All you have to do is look at those factors and think, well, what number would make those factors equal 0? So in this case, we've got x minus 1 times x plus 3 squared. That is a third-degree polynomial. And so the three zeros of that polynomial are really easy to see. Positive 1, negative 3, and negative 3. And yeah, you don't really have to write the negative 3 twice, but I do just to illustrate the fact that there are, in fact, three zeros for that polynomial. Let's take a look at another one. P of x equals negative x times x plus 5 times 2x minus 3 squared. All right? So this is a fourth-degree polynomial. And by looking again at those factors, including the little x out there by itself, we can see that 0 is a factor. That is, 0 is a 0 of this polynomial. And it's got 4 of them, being a fourth-degree polynomial. And by looking at the factors, you can once again see that 0, negative 5, and 3 halves are the zeros of this polynomial. Well, what happens, though, when it's not in factored form, such as this one right here? Well, it's not really a factored form yet, so you have to do a little bit of work. And by right away, you can see that if you can factor out a 2x squared from each one of those terms. And if you do, what that does, that gives you a quadratic factor that can itself be factored into x plus 2 times x minus 1. And you can check that if you'd like. But there it is in factored form. It's a fourth degree, obviously, and the 4 zeros of this polynomial are 0, 0, and negative 2, and 1. I listed the 0 twice since it's the x squared out there. All right? But factoring, it's really nice, but it doesn't always give you all the zeros. Here's another polynomial, fourth degree polynomial, and it cannot be factored completely just by normal ways. But I do see that it can be factored a little bit at least. I can take out an x from everything, and that's going to give me one of the zeros right there. That x by itself will give me one of the zeros. X equals 0. Once again, is a factor of is a 0 of this polynomial. The other factor, though, that cannot be factored anymore. So what I have to do is I have to use the synthetic division process. So I'll set those numbers, those coefficients, in my synthetic division little arrangement here, and then the question is over there, what do I put out there? What am I going to try to divide this by? And if you recall, the rational zeros theorem says that you want to take the factors of the constant, in this case 15, and divide them by the factors of the leading coefficient, which in this case is 1. So 15 divided by 1, and that's all the factors that we need to consider there for our possible rational zeros. If I do that, I get plus or minus 1, 3, 5, and 15. And probably won't have to deal with 15. But anyway, let's try negative 3 and see how that works. All right, so here's the synthetic division algorithm. So if it's still kind of a fuzzy thing for you, pay close attention here. To do the synthetic division process, having already chosen my divisor of negative 3, draw the little line there, and I bring down the 1 unchanged. I multiply my divisor. I multiply negative 3 times 1, and I write that right there underneath the next coefficient. I add them up to get negative 6. I multiply the negative 6 times the divisor, negative 3. That gives me positive 18. Now I add those together. The negative 13 and 18 gives me positive 5. I multiply the negative 3 times the 5, and that gives me negative 15, which gives me a remainder of 0. Hallelujah. All right, so I do know now that x equals negative 3 is another 0 of this polynomial. So I got 2 down and 2 more to go. Well, my quotient here at the end of that synthetic division process is a quadratic quotient. All right, and when you end up there with a quadratic quotient, no matter how long it takes you to get there, that's pretty much where synthetic division ends. Because that quotient right there is really x squared minus 6x plus 5, which can be factored into x minus 1 times x minus 5. So there, right in front of me there, are the remaining two zeros of this polynomial. All right, x equals 1, x equals 5, and now I have all four zeros of this polynomial, 0, negative 3, 1, and 5. Wasn't that great? Okay, well, just keep in mind now, when you end up with this quadratic quotient at the end of the synthetic division process, it's not always factorable like this one was, all right? Sometimes you may have to use the quadratic formula to find the remaining two zeros of your polynomial, and those could be irrational numbers, or they could even be complex numbers, imaginary numbers. So there's a lot more to this process here than I really have time for. That's almost 6 minutes, and we're going to stop there. Next topic, asymptotes of a rational function. Okie dokie. Alrighty, here we are for the last topic here. This one is going to be asymptotes of a rational function. All right, we are going to look at three kinds of asymptotes, like we did in class: vertical asymptotes, horizontal asymptotes, and finally oblique asymptotes. All right, so let's get started. We'll take a look at vertical asymptotes first. Okay, not really going to get too much in the way of examples here. Just want to mention to you that the vertical asymptotes are of a rational function, if they exist, are found by finding the zeros of the denominator. If you find those numbers, the numbers that make the denominator equal 0, you have just found located the vertical asymptotes for that function. All right. Let's see, there's something missing here. Oh yeah, there it is. All right, so let's talk about then horizontal asymptotes. They're a little bit more involved. Not really take a lot of work though to find them. Because the reason that you find these, the way that you find horizontal asymptotes is to compare the degrees of the numerator and the denominator. That's all you have to do, is to compare the degree. And if you think about that, there's really only three situations possible. The first situation is if the numerator's degree is greater than the denominator's degree. In that case, there is no horizontal asymptote. So that's pretty easy. The next possibility is if the denominator's degree is greater than the numerator's degree, right? That's another possible scenario there. And in that case, the horizontal asymptote is the equation y equals 0. Okay, so that's not too bad. Last possible situation that could exist in comparing those degrees is if the numerator and denominator have the same degree. And in that case, the horizontal asymptote is the ratio of the leading coefficients. All right, we'll show you what that looks like a little bit later on. So that's how you find the horizontal asymptotes, is by comparing the degrees. All right, last little topic here is I've got an example here for you of these horizontal asymptotes, and the first one has a numerator with a degree higher than the denominator. In that case, there is no horizontal asymptote. All right, here's another example. If you had a rational function where the numerator's degree was less than the denominator's degree, all right, in that case, the horizontal asymptote is y equals 0. So there's a couple of examples there. Now the last example is this right here. We have a rational function where the degree on top is the same as it is on the bottom. So you just look at those leading coefficients. In this case, it's 5x minus 1 over 2x plus 1. And so the 5 over the 2, that's the ratio of leading coefficients. Therefore, the horizontal asymptote is y equals 5/2. Okay? So there's the deal with horizontal asymptotes, if they even exist. The third and final kind of asymptote that we're going to talk about, you may be wondering why I always use this y equals form, because horizontal lines always have this simple looking equation, y equals k, y equals some number. Alrighty? So finally, the last type of asymptote that we're going to look at are oblique asymptotes. All right. Now they don't always happen in a function. If they do happen, they happen only if the numerator's degree is one more than the denominator's degree. All right. So you compare the degrees once again, and if it's 1 greater on top than it is on the bottom, then there is an oblique asymptote. And I'm going to bring back that rational function that we had a little while ago, 2x squared minus 3x over x minus 5. The degree on the top is 2, the degree on the bottom is only 1. So there is an oblique asymptote for this rational function, along with a vertical asymptote at x equals 5. But there's an oblique asymptote, and the way you find that oblique asymptote's equation is to actually perform the division of the fraction, the polynomial division. So 2x squared minus 3x divided by x minus 5. And when you do that division, all right, you kind of work that through, we wind up with a quotient on top of 2x plus 7. All right, and that quotient is actually the equation of the oblique asymptote. All right, so it's a little bit of work, but it's really not too bad. You just do the polynomial division of the fraction itself, and the quotient you get is the oblique asymptote. All right. Well, I think that's about enough for asymptotes there. Makes this video pretty long here. So hope you hung in there with the whole thing, and be sure to do the little online quiz following this video. Okay, take care. Bye-bye.